Hello, fifth graders. This is our second video about the topic of prime numbers. And right away, I'm going to introduce you to the fundamental theorem of arithmetic. The word fundamental means extremely important. This is an extremely important concept about the whole numbers. And the fundamental theorem of arithmetic says that every whole number greater than 1 has a unique prime factorization, not counting order. Unique means only 1. So now we have to understand what this prime factorization, what is that all about? Well, we've already talked about what the factors of a whole number are. And I decided to start with the whole number 24. Let's first identify what we're not being asked to do with the 24. We're not being asked to identify all of its factors. Now, rather than write them on the board, I think it's that you'll be able to agree with me, just if I say that the factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4 and 6. Remember in that previous video about factors, I suggested you start with 1 and the number and then work your way toward the middle. So in order, all of the factors of 24 would be 1, 2, 3, 4, 6, 8, 12, and 24. Right? That's just restating in order those pairs of factors. Those are all of the factors of 24. But what is the prime factorization of 24? Well, it's representing 24 as the product of whole numbers that are only prime. Product, of course, means multiply. The product of 4 and 6 is 24, which is why 4 and 6 are factors of 24. So let's do this. Let's write beneath the 24 a 6 and a 4. Now, 4 times 6 is 24. What I am starting to do here is to construct a tool known as a factor tree. It's called a factor tree because it has branches. I branched off of 24 with a 4 and a 6. And I can do that because 4 times 6 is 24. But then I look at the 4 and the 6 and I realize neither one of them is prime. I want to keep going with the branches until I have only prime numbers. So from the 4, of course, I can branch off to a 2 and a 2. And from the 6, I can branch off to a 2 and a 3. 2 is prime, 3 is prime. So often I have students circle these prime numbers that we end up with. We end up with 3 2s and a 3. So what we can do is we can go back here to the 24 and say that 24 is 2 times 2 times 2 times 3. Make sure you agree that when you do 2 times 2 times 2 times 3, you get 24. And further, the 2 and the 3, both of them are prime. 2 times 2 is 4, times 2 is 8, times 3 is 24. Now, we've learned about exponents. Exponents allow us to abbreviate. That's all really that exponents do. This 2 times 2 times 2 can be abbreviated or written using exponents as 2 to the third power, right? So 2 to the third power times 3. We're going to agree, just to make things look pretty, as I like to say, to make things look pretty or nice, we're going to agree to put the prime factors in order from least to greatest. You don't have to, but I put the 2's first and then the 3, so least to greatest, and then use exponents if we have more than one particular prime number. All right? This is what's known as the prime factorization of 24. And it is unique. The only way you can represent 24 as the product of only prime numbers is 2 to the third times 3. That's what the fundamental theorem of arithmetic says. Now, the fundamental theorem of arithmetic is one of those handful of items that I will not be able to prove to you. I'd have to refresh my memory myself Right now, I could not prove the fundamental theorem of arithmetic. I've read proofs of it, and I think I understood them when I read them, but they're a little bit too sophisticated for 5th grade. So it's one of the few items I'm going to ask you to accept on faith that it is true for all whole numbers. I'm going to kind of give you an idea that it's true for 24 right now by doing this. Let's say we start with 24 again, except this time, as our first step, rather than starting with 4 and 6, let's start with 3 and 8. 3 times 8 is also 24, right? But we look here and we say, well, the 3 is prime. Once we get to a prime number in our factor tree, when we're branching off, we'll circle it, and we don't go any further. And then the 8 is not prime. 8 is 2 times 4. 2 is prime, we'll circle it. The 4 is not prime. 4 is 2 times 2. Do you see what happened? I went about it differently. I started with 3 and 8 rather than 4 and 6, but I still ended up with 3 2s and a 3. So I would come up and do the same thing that I did before. This prime factorization of 24 is unique, no matter how you go about it, and you could have started with 2 times 12 and still gotten to the same single result. Prime factorization of 24 is unique. There is no other. It's 2 to the 3rd times 3. Let's look at 2 other whole numbers greater than 1 and ask, what is that number's prime factorization? Well, in many areas of math, whether you're in 1st grade or college, some problems are easier than others. Some questions you can answer more quickly than others. If you ask, what is the prime factorization of 35? You start a factor tree, for example, and you try to think of 2 numbers that multiply to 35. Well, 5 and 7 should immediately come to mind. Well, 5 and 7 are each prime, right? We circle them. We can go back up here and say that 35 is 5 times 7. Now that's obviously true, you know that. But one thing that you weren't aware of until now is that 5 times 7 is not only a factorization of 35, it is the prime factorization of 35, because 5 and 7 are both prime. And we're done. Let's try 140. Now, I would suggest that there are several factors of 140 that should be obvious to you. Maybe the most obvious, hard to say, it's different for everybody, but when a whole number ends in 0, it has 10 as a factor. 140 is 10 times 14, right? Neither one of these is prime. So 10 times 14 is a factorization of 140, but it's not the prime factorization of 140. We have to continue the so-called factor tree until we end up with only prime numbers. 14 is 2 times 7. Both of those are prime. So we circle them. 10 is 2 times 5. Both of them are prime. So we're done. All we have to do, though, and when I ask you to find prime factorizations, don't stop here. Show me you know what that result means. And let's agree, just to make it look nice, and all of our answers look the same, that we will put the prime factors in order from least to greatest with time signs between them. The whole point of this is we're talking about factorization. Factorization indicates multiplication, and we will abbreviate with exponents. But prior to abbreviating with exponents, we would have 2 times 2 times 5 times 7. Those are the prime numbers that we ended up with. 2 2s, a 5, and a 7. We can abbreviate this as 2 to the 2 power times 5 times 7. So that's how we'll express the prime factorization of 140. Let's confirm that it's true at this level here. 2 times 2 is 4, times 5 is 20, and then times 7 is 140. Now, that sort of makes me think immediately, see what I just did? 2 times 2 is 4, times 5 is 20, and then times 7. Remember before I said there were a lot of factors of 140 that should come right to your mind? Well, this one might have come to your mind. 20 times 7 is 140. If you had started with 20 times 7, you would end up with the same prime factorization. That's what the fundamental theorem of arithmetic says. We've got the 7. Can't go any further on that branch, right? 7 is prime. 20, now here you can do 2 times 10 or 4 times 5. It doesn't matter. I'm not going to show you all possibilities because there are a lot of them, all possible ways to make a factor tree. But what I'm trying to convince you of is that no matter how you go about it, you will always get the same result. Let's take 4 times 5. 5 is prime, so we'll circle it. And then the 4 is not prime. The 4 is 2 times 2. So there's the same answer. 2 2s, a 5, and a 7. Just like we got before using 14 and 10. Maybe the most obvious factorization for some of you of 140 would be 2 times 70. Well, you try this on your own. 2 times 70. Circle the 2. Continuing with the 70, I guarantee that you're going to get the same result that we got the other 2 ways. There's only one result for the question of what is the prime factorization of 140. No matter how you do it, it's always going to be 2 squared times 5 times 7. And that goes back to this word unique. The word unique means there's only one. Now, notice in the definition of the statement of the fundamental theorem of arithmetic, I said not counting order. In other words, someone could say, well, it's 2 times 2 times 5 times 7, or it's 2 times 5 times 7 times 2. Of course, we could rearrange the order of the factors, but that's why we say not counting order. There's only one way to do it. Even something as simple as 35, you could have expressed it as 5 times 7 or 7 times 5, but we say that that's unique, even though we could change the order. So not counting the order, the prime factorization is unique. One last thing I want to say before I go on to some other numbers to deal with some other things. When I chose 35 and 40, I did something on purpose. 140 is a multiple of 35. 35 is a factor of 140. Let's ask this question and answer it. What do you multiply 35 by to get 140? It's a whole number. You should be able to come up with it. Think about it for a minute. What can you multiply 35 by to get 140? It's a relatively small whole number. It's 4, right? 35 times 4 is 140. 4 times 30 is 120. 4 times 5 is 20, and put them together. 120 plus 20 is 140. So 35 times 4 is 140. Now let's go back to the prime factorization of 35. What was that? 5 times 7. And what's the prime factorization of 4? 2 times 2. And there it is. This is the prime factorization of 140. Does that make sense to you? It should. Play this as often as you need to until you get to that point where you understand, where you say, of course, it has to be that way. It makes sense. Don't just try to memorize things. Get to the point where the math is understandable, something that you agree must be true. And as you young people like to say, you get it. If you don't get this fact, this what I just tried to convince you of, You know, we had the 35 and the 140. I chose them specifically because I knew that, in fact, I got the 140 by doing 35 times 4. That's how I chose the 140. I decided to go with 35, and then I multiplied it by 4 to get 140. So that I could then come and point out to you, well, 35 times 4 is 140, and the 35 is 5 times 7, the 4 is 2 times 2, and this has to be 140, and it is. All right. Remember our old friend, 17? Yes, 17 was a number we talked about in the video about factors, finding the factors, all the factors of a whole number, and then indicating the multiples. You can never write all the multiples of any whole number because there are an infinite number of them. But when we were dealing with that video on factors and multiples, I kind of ended with, all right, what are all of the factors of 17? And of course, there are only 1 and 17. And then in the next video I said, there's a name for those kind of numbers, we call them primes. So 17 is prime. Well, that raises the question now with this fundamental theorem of arithmetic, what is the prime factorization of 17? Well, this is about as easy of a question as you can be asked. All you have to do is, there it is. So think about it. This is the only way we could handle a prime number in terms of the fundamental theorem of arithmetic. A prime number is its own prime factorization. Okay? That's all we can do. So that's a little bit of a, I thought about including that as part of the statement of the fundamental theorem of arithmetic, but I figured instead that we would just come to this conclusion together, right? So if we were to, if I were to continue the statement of the fundamental theorem of arithmetic, I would say prime numbers are their own prime factorization, because that's all we can do. Now, let's talk about dividing the whole numbers into 3 groups. Let me remind you that the whole numbers, they are the numbers that we all learn about when we're very young. 0, 1, 2, 3, 4, 5, and so on, going on forever. These are the whole numbers. So we're going to think of them as being in 3 categories. All of the whole numbers are in 3 categories. One of those categories or groups is 0 and 1. And what we say about 0 and 1 is they're special. They're in a group or a class by themselves. And then all the rest of them, there are 2 groups other than 0 and 1. There are the primes, which of course, as we know, begin with 2 and 3 and 5 and 7 and 11 and 13, and they go on forever. Okay? And then there are the composite numbers. The composite numbers would be 4, 6, 8, 9, 12, 14, 15 is composite, right? So we say that 0 and 1 are special in a group of their own. And remember, the definition of prime said a whole number greater than 1. And in the fundamental theorem of arithmetic, we say every whole number greater than 1 has a unique prime factorization. And in defining composite numbers, what did we say a composite number was? A composite number is a whole number greater than 1 that's not prime. Okay, so you single out the primes, as we've done, and then all the other whole numbers greater than 1 that are not prime are called composite. And why is that? Well, you know, a composite number would be 35. It's composite because it's made up of 2 primes multiplied together. It's 5 times 7. 35 is sort of made up of a 5 times a 7. It's made up of 2 primes multiplied together. And those are the only 2 primes that multiply to 35. That's the fundamental theorem of arithmetic. Now let's talk a little bit about 0 and 1. Well, let's eliminate 0. How many factors does 0 have? How many whole numbers are there that you could multiply 0 by? Let me phrase it this way. How many whole numbers are there that multiply to 0? There are an infinite number of them. And one of them has to be 0. 0 times 1, 0 times 2, 0 times 3, 0 times 1,000, 0 times a million, they're all 0. So 0 is kind of uninteresting in that regard, right? In terms of factors. Any whole number, any number times 0 is 0. So 0 has an infinite number of factors. So that's why we're excluding 0. Why do we exclude 1? I mentioned this earlier in a previous video. You know, it's a very logical thing for someone to say, a young person like yourself. Well, why isn't 1 prime? The only two factors of 1 are 1 times 1. That's true. But we exclude 1 from being a prime number for a very practical reason, so that we can have a fundamental theorem of arithmetic. Let's say that 1 were prime. Let's say we're going to consider the number 1 to be prime. Well, the prime factorization of 35 could then be 1 times 5 times 7. And then there would be 2 of them. The prime factorization would not be unique. In fact, we could say if 1 were prime, 1 is not prime, and I'm explaining now, right now, why 1 is not prime. Because 35 could be represented as 1 times 5 times 7. And in fact, there would be an infinite number of prime factorizations of 35 if 1 were prime, because we could say 35 is 1 times 1 times 1 times 1, any number of 1s we want times 5 times 7. So sometimes in math, the rules that we set up, the definitions, in this case, the definition of a prime number, remember, greater than 1. Why greater than 1? Well, you have to get to this idea of the fundamental theorem of arithmetic before you understand why we exclude 1. We exclude 1 for a very practical reason, so that we would have a fundamental theorem of arithmetic. It's as simple as that. Sometimes math is pragmatic, meaning it's set up the way that it is so that it works in a nice way. I'm going to close this video by trying to convince you of why we call the prime numbers the building blocks of the whole numbers with respect to multiplication. There's more that we can do with prime numbers, more questions that we can ask, and cool things that we can look at. In terms of the fundamental theorem of arithmetic, we will practice. I will give you in class or for homework, and eventually on quizzes, I'll say, find the prime factorization of a particular number. And I will always do that in a way where it's reasonable. Some will be harder than others, take longer than others, but it'll always be something that you should be able to do. You've seen some examples here. There will be more examples where I give you a whole number, and your job is to come up with the prime factorization of that number, and there will only be one. It's unique. So that will come. We will work more with prime numbers, but as I said, I want to give you this concept of the prime numbers being the building blocks of all the whole numbers with respect to multiplication. Now, let me first indicate what the building block is for all the whole numbers with respect to addition. And this is a very obvious and kind of boring thing, but it's important that you understand it. What is the building block of all of the whole numbers with respect to addition? You want to take a guess at what it is? It's a number. What number can we build all of the whole numbers with by adding? A single number. With the prime numbers and multiplication, there are an infinite number of prime numbers, so an infinite number of building blocks for the whole numbers with respect to multiplication. But with respect to addition, it's only one number, and it is one number, the number 1. Okay? If you were guessing that a moment ago, you're absolutely right. So we can't really consider 0 when we're talking about the building blocks of the whole numbers with respect to addition. We could just say 0 is a whole number and that would be it. But for all the others, we can say that the building block is 1. Well, there's 1. All right. Now, what about 2? There's 2. 1 plus 1. What about the next whole number, 3? 1 plus 1 plus 1. You see how boring this is? But it's an important concept. Very obvious. Every whole number can be thought of as a sum of 1s. Let me indicate this sort of symbolically. Dot, 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 1. And let me put down here 107. What if we had 107 1s added together? 1 plus 1 plus 1 plus 1 plus 1, 107 of them. What would that be? Well, obviously it's 107, right? So this is how we can say that 1 is the building block of all the whole numbers 1 and bigger. I guess you can't think of 1 as a building block of 0, but 0 is special, as we said before. Okay, now you cannot use 1 as a building block for all the whole numbers with multiplication. Because if I replace these plus signs with times signs, okay, let's do that. Let's say 1 times 1 and 107 1s. That's not 107, that's 1 if those are times signs, right? So we need something else to build all the whole numbers with multiplication, and that's the prime numbers. So I'm going to do something here which is kind of fun. You might want to continue this on a piece of paper and show me someday. I wouldn't mind taking a look at it, as long as you don't go too high, because, you know, could get a little tricky as we go higher. But, all right, let's indicate the whole numbers in a new way. All the whole numbers, all right? Now, 0 and 1 are whole numbers. They're special. I'll just put them here. And now, what we're going to do is, we're going to use the fundamental theorem of arithmetic to write all the other whole numbers with only primes. The next whole number after 1 is 2, and then 3, okay? Now, 0 and 1 are special. We have to start with them for the whole numbers, but then the next whole number is 2. 2 is prime, so I wrote 2. Next whole number is 3. 3 is prime, so I wrote 3. But I'm not going to write 4. 4 is not prime. But 4 has a prime factorization, which is obviously 2 times 2. So instead of writing 4, I'm going to write 2 times 2. Down here, just to remind us of this fact, what I'm doing is I'm indicating all of the whole numbers. But I'm doing it without using any composite numbers. So instead of 4, I wrote 2 times 2. Now after 4 comes 5, which I will write there, but I'm not going to write 6, because 6 is not prime. What is the prime factorization of 6? 6 is 2 times 3. So instead of 6, I'm going to write 2 times 3. Down here I'll write 6 just to remind us, right? 0, 1, 2, 3, 4, 5, 6. But I'm indicating the whole numbers, all of the whole numbers, with either a prime, like 3 or 5 or 2, or if it's not prime, I'm going to write its prime factorization, which we just learned about. Okay, come down to this next line here. I always have a problem with markers that don't work. Run out. I think you can see all of that. Let me try this one. After 6 comes 7. I'll write 7 because it's prime. It's its own prime factorization. The next whole number after 7 is 8. Now 8 is not prime. Is it all right if I just write 2 to the third power? Now I could have written, and this is 8, I could have written 2 times 2 times 2. That's 8. But we can abbreviate 2 times 2 times 2 is 2 to the third. So that's 8. The next whole number after 8 is 9. 9 is not prime. I'm going to write here 3 to the 2 power. 3 times 3 is 9. Do you see what I'm doing here? Every single whole number is being written as its prime factorization, with the understanding that a prime number is its own prime factorization. We'll see that in a moment. The next whole number after 9 is 10, but I'm not going to write 10. I'm going to write 2 times 5. The prime factorization of 10 is 2 times 5, right? So that's the 10. Now, the next whole number after 10 is 11. I'll just write 11. Why? Because 11 is prime. It's its own prime factorization. 12, the next whole number is 12. 12 is 2 times 2 times 3. I'm going to write it using the abbreviation of exponents, 2 to the 2 power times 3. That's 12. 2 to the 2 power means 2 times 2. That's 4 times 3 is 12. This is the prime factorization of 12. The next whole number after 12 is 13. So I'll write 13. After 13 comes 14. 14 is obviously not prime, but it's 2 times 7. Its prime factorization is pretty obvious. There's the 14. Next comes 15. 15 is 3 times 5. The prime factorization of 15 is 3 times 5. Do you appreciate that I could continue like this forever? Indicating all of the whole numbers by their prime factorizations. All the whole numbers greater than 1, because again, 0 and 1 are special. Now, for 5th graders, ladies and gentlemen, this is kind of sophisticated. This is a very sophisticated concept for new 5th graders. This fundamental theorem of arithmetic, and that every whole number can be thought of as the product of prime. Every whole number greater than 1 is either prime or the product of prime. So this is why we can think of the prime numbers as being the building blocks. They are the building blocks of all the whole numbers greater than 1 in terms of multiplication. And I hope you agree with me, that's a lot more interesting than thinking of 1, the number 1, as being the building block of all the whole numbers with respect to addition. Right? This is a little bit more interesting to consider. At some point, if we continue here, let me go dot, dot, dot. At some point, I would have to indicate, well, let's do this. Let's do 99 and also 100. Some of you may be able to appreciate this right now. I'm skipping ahead here. I'm skipping 16, 17, so on, all the way up to, let's indicate 99. Can I put 99 on this list of the whole numbers only using primes? The answer is no. 99 is not prime. 99, you might immediately recognize it as 9 times 11, but I cannot write 9 times 11 because the 9 is not prime. But here's what I can write for 99. I can write 3 squared times 11. 3 to the 2 power times 11. That's 99. This is the prime factorization of 99, right? 3 to the 2 power, 3 times 3 is 9, times 11 is 99. At some point in the future, I'm going to talk about the prime factorizations of the powers of 10. Every power of 10 has a prime factorization that's easy to identify. For right now, I'm just going to close this video by indicating to you that 100, now 100 is obviously not prime. Here's its prime factorization. 2 to the 2 power times 5 to the 2 power. Now you can appreciate that that's true. There's sort of a pattern to the prime factorizations of all the powers of 10. This 100 here is a power of 10. It's 10 to the 2 power, right? 10 to the 2 power is 100. And its prime factorization is 2 to the 2 power times 5 to the 2 power. We'll explore this pattern a little bit more in the future, but let's just make sure everybody agrees. What's 2 to the 2 power? That's 2 times 2, it's 4. And what's 5 to the 2 power? 5 times 5, 25. 4 times 25 is 100. So that is the prime factorization of 100. Prime numbers, the fundamental theorem of arithmetic, these are important topics in what is known as number theory. Number theory is, I'm going to be honest, only a small part of 5th grade math. 5th grade math is much more concerned with, in terms of the time we spend, with fractions and decimals and calculating with fractions and decimals. But this is an important part of math in general, the area of math known as number theory. And it's fun, and I would suggest easy. So enjoy the entire journey. So long for now, 5th graders.